Alrighty, so let's do the approximate molar solubility of calcium carbonate in 0.2 molar calcium chloride. Now the molar solubility means that I'm looking for something that's going to be in terms of molarity, which means that I'm missing a KSP value. On your exam, I will give it to you. This was homework. This was stuff you were doing ahead of time. It wasn't unreasonable to make sure that you went and looked this up, but you're going to have to find a KSP value for it. On an exam, I would either give you a table or put it in the question itself. So I'm going to be able to use this KSP that I just looked up, and as a note, you'll find 92 different values for that KSP in 92 different tables. This is the one that I found in one of the tables, so it's the one that I'm going to use for this. It's probably different than your book, and your book may be different even than what's given to you in OWL. So if your final answer doesn't look exactly like mine, it's probably because your KSP doesn't look exactly like mine. Now, if I set up the equilibrium between calcium carbonate, which is a solid, and its ions, which is calcium 2+, which happens to now be aqueous, and carbonate 2-, which also happens to now be aqueous, right? I could set up an ice table for this, and since I'm calculating the molar solubility of it, that's probably the thing I need the ice table for. But I also have to remember that in this same solution, there's a second equilibrium that's happening. And it's a really product-favored equilibrium, so I should probably draw it more like that. But still a competing process that I have to deal with. And that's that calcium falls apart to its ions. Now, the chloride in this competing equilibrium doesn't matter because the chloride's nowhere in my calcium carbonate equilibrium. But I do have a calcium here that is also here. So at equilibrium, I'm going to make some calcium ion from the calcium carbonate, but I'm also going to have additional calcium ion floating around from that calcium chloride. And I'm going to have to take both of those into account when I figure out the molar solubility. Now, to figure out the calcium from the calcium chloride, that's relatively simple. Since it's a strong electrolyte, it's going to dissociate in solution. And since it's a 1-to-1 ratio, whatever the concentration of the calcium chloride was will be the same as the concentration of the calcium itself. I'm going to need this in a minute when I get to the equilibrium line of my ice table. Now let's go back to the calcium carbonate, and let's put some lines here because these are solids and we don't care. And let's remember that initially I'm not going to have any of those ions. I haven't made anything yet, so they're just not formed yet. That means that my plus X, or S, if you happen to like S better, right? That's going to go on that product side. At equilibrium, from the calcium carbonate, I end up with S and S. I'll just go ahead and use the solubility notation that we had in the other video. Now my KSP expression is going to be equal to calcium 2+, carbonate 2-. And its concentrations of each of those. No stoichiometric coefficients needed, so no superscripts needed. I know the value of the KSP, so I can plug that in. I know that calcium is equal to S from the calcium carbonate, but it's also equal to 0.2 from the calcium chloride. So I have to take both of those into account when I set up my KSP. The carbonate's just S, so it's really no big deal. Now again, some of that calcium in solution is coming from the calcium carbonate. And so any other equilibrium constant that we've done before, you would just bring the S into the KSP expression, so that's not new. What's new is also taking this counter ion and putting that counter ion in the same solution. Now, if I look at the difference between this KSP and this concentration here, the difference between those two values is much, much greater than 5%. So we can use that same 5% rule that we've been using all semester. That 5% rule said that if the quantity I'm solving for, in this case S, is much, much smaller than the quantity I'm starting with, in this case 0.2, then I can probably just drop that S and simplify my algebra. And so I'm going to do that here. I'm going to drop that S. That gives me a value of 0.2. I still have to keep the S for the carbonate because there's no competing ions for it. The only carbonate I have is from that calcium carbonate. So now I have something relatively simple. I can just divide the KSP by that 0.2, and that should give me a value of S 7.0 times 10 to the minus 8 molar.